Today we are going to talk about the work done on a stretched wire or an elastic material, such a substance in which it will recover its original dimension or the original shape when it is being distorted or when a force acts on it, a force or when I say a stress acts on the material. Now, in order to stretch a material, suppose that we have a wire. If you exert a tensile stress is meant to elongate a substance. If you exert it on this material and you pull it towards this direction, if the change in the new length, if there is an additional length, let's call that x. Now, because it is downward because it is downward in this case, our f that we use can be equal to mg. It could probably be because you put a load, something like this. Maybe this is the wire, then you may have a load here. The load, if it is 5 kg, the acceleration due to gravity will also help it. So the weight will eventually be measured instead of the force, which is mg. And that's why F is equals to mg in this case. Okay, but before I continue with this, I would like to quickly define what energy stored in an elastic material is. When you are stretching a wire, certain work must be done against the internal restoring force. While stretching this wire, the internal force are actually at their equilibrium position. So by stretching the wire externally, you are distorting the material by because the internal molecules of the material will have to rearrange themselves in order to fit in the new dimension that you want to cause. As a result, the work done against the restoring force is referred to as the energy stored in the elastic material. This work done is stored in the form of potential energy U, or the elastic potential energy of the stretched wire, and is referred to as the strain energy. The energy stored per unit volume of a stretched wire is called the energy density. Now, let's continue with this. Now, the small work that is being done on the material, let's call it dW, which is the product of force through the small distance. This is the force that is being exerted. When you exert the force gives birth to the work that is being done because the force is against the internal restoring force. As a result, the total work done, W, that is needed in order to elongate the wire is done by integrating from 0 to x. That is, we are integrating through this length, through it. So we can have something of this nature, f dx. Okay, but note that the formula for f, we can get it from the expression of the Young modulus. Given that the Young modulus is stress to strain, and stress is force over area divided by the change in the length. The new change in this case is x, and the original length is L. So as a result, we have the force upon the area multiplied by the length upon the x. That is, by removing the division, so I now have multiplication. So what I want to do is I want to make f the subject of the formula. So in this case, I will have the Young modulus a x all over L, which is equal to f. So if I substitute that into this expression, I will have w, which is equal to the integral from 0 to x. Then f, our f in this case is the Young modulus, the a, the l of x all over. Then I will have dx. In this case, these are all constants, so I will just bring them out of the integral. So I will have the Young modulus a upon l, the integral from 0 to x, then x dx. If I integrate this, I will have something of this nature. The Young modulus a, then x squared upon 2 all over l, which is equal to the work that is being done. Is the same as if I have Young modulus a x dot x, since we have 2x, then over 2l. Yax, that is over l, yax over l is the same thing as f according to this. So we can have something of this nature. Okay, let me just circle that. Yax over l is the same thing as force. So we can have 1 over 2 fx. So it means that the work done that is being required to elongate the material is the average force multiplied by the extension. So we can have it something of this nature. The average force is the product of the average force and the elongation. So this is the formula for the work done that is being required to stretch a wire. Note that F, this F is also equals to KE according to Hooke's law. It means that W is equals to half K. Okay, in this case, instead of using E, I'll use X. Since E and X are the same, it means the same is the extension. But in my case, I use X. So I will have half KX squared. Alright, so this is the formula to find the work done on a stressed string. This can also be done. I can also obtain this formula from the graph of a load extension graph, provided the elastic limit is not exceeded. Let's do that. Provided the elastic limit is not exceeded. If we draw a force extension graph, force extension delta x or x, in our case we used x in the other formula. Provided the elastic limit is not exceeded, I explained what elastic limit is and some other things that will happen when you are trying to plot the load versus the extension graph. There are a lot of stages that the material will go through on this in this relationship. In this relationship, there are a lot of stages that the material will go through. I explained it in this video. Check this video. Suppose that the elastic limit is not exceeded, it means that I will just have a linear, I explained it in that video, I will have a linear relationship. Since the elastic limit is not exceeded, then I will have something of this nature. So let's assume this is point A and this is point B, and this is the F that is required to get to this point, the force that is required for the material to get to this point. So the area of this graph will give us the work done. Now, the energy stored is the area of the shaded portion within the elastic limits. That's it. That is, the area is equals to triangle OAB. And the area of triangle OAB is half AB times OB, and that's equals to half Fe, which is the same thing as half Ke squared. In this case, I used delta x, which is the same thing as e. So I think I'll prefer to just go with 1. So that's that e is the same thing as delta x. All right.